Hello everyone. Today we'll talk about Taming Normalizing Flows, which is a novel way to change your generative model, specifically a Normalizing Flow model, to produce more or less of a specific identity or a concept or a property. First, a quick note, if you are seeing this in the future, it is now the end of 2023. Israel is at war, and Shimon, who did all of the work on this project, got drafted to the army. So that's why I'm giving the presentation. It will be a short one, and hopefully it will give you the gist of the work and convince you to check out our code and paper for more details. Let's start with some motivation. There's been tremendous progress in generative models, Gen AI, in the past few years. For example, here we see Imagen and DALL-E 2. They produce highly photorealistic results, really high quality, and nowadays they are even better and newer models. However, there are also issues with these models. For example, DALL-E 2, when it came out, it used to output mostly males when you asked for a CEO. After these results were created, since then, there have been mitigations. Nowadays, when you ask for CEOs from DALL-E, you should get both males and females. But still, it's far from perfect. Besides the biasing, there are other cases where you want to tweak the output of a generative model, for example, to censor unsavory content or to make specific people appear more or less, for example, for privacy concerns. Which leads us to the goal of our work. We want to control the output probabilities of generative models with respect to some rules or data. Most outputs should remain the same, but some should change according to our intent. For example, here we have a generative model of faces, and we want the model to generate all identities except for Stephen Colbert. The model was initially trained to produce Stephen. We want the model to forget him. This also ties into the EU's right to be forgotten, if you heard about that. Okay, so how do we do this? First, we need to briefly talk about normalizing flows. The key idea behind these models is to use an invertible function. During training, we map out data to a normal distribution, and during inference, we sample from the normal distribution, which is easy, and use the inverse function to convert our Gaussian sample into an output. Okay, so our problem definition. Given a pre-trained normalizing flow, a set of images to forget or de-emphasize, and a set of images to remember. These images are images that are supposed to represent the distribution that we wish to preserve. For example, it can be a subset of the training data, but not necessarily so. Given all of these, we want to output a new model that does not produce the forget set or produces it at a given probability specified by us, preserves the distribution globally, so meaning that not specifically keeping likelihood of every instance the same, but rather to keep the entire distribution the same, the entire output distribution. And the third goal is to preserve the general quality of the output, obviously. Let's continue with our example. We can think of each Gaussian here as images of some person, right? So we have 5 people. In the original training of the network, all 5 people were part of the data, and all of them appear in the Gaussian which we sample from, thus are likely to appear as output. Now let's say we want to forget the orange person. Our procedure pushes the orange dots to a very unlikely place of the distribution, like it's a Gaussian, remember? Thus, when we sample from the Gaussian and convert to outputs, it is very unlikely that we'll get the orange person. And indeed, we see that when sampling many times, we get 4 clusters, and we successfully forgot the 5th orange cluster. Here we show the progression of this process over time. After around 100 iterations, we successfully forget the orange cluster. At this point, you might be thinking, okay, fine, but there's a very naive solution. Let's assume we have the original training data. In this case, the naive solution is to retrain the network from scratch using the training data minus the forget set. Okay? The trick is that this takes a lot of time, and we want to find a fine-tuning procedure over the existing network that achieves the same result, but much, much, much faster. I'll now briefly explain our method, and please refer to the paper for more details. First, throughout the taming process, we can estimate the negative log likelihood of the data. Why can we do that? Because we are dealing with normalizing flows. That's important because using the negative log likelihood, we can now push images from the forget set towards a specific threshold value of likelihood. This is what we minimize. Our second goal is to make sure we preserve the output distribution of the original network minus the forget set. So here we have two negative log likelihood curves, one for the remember set on the original base model and the other on the tamed model, which changes throughout the taming procedure. We want the two to be as similar as possible. How do we do that? Using both an explicit method and an implicit method. Explicitly, we use the KL divergence between the two distributions. So this is a loss which is explicit, which forces the distributions to be similar. Implicitly, we use the regular normalizing flow loss. We essentially mimic the original training procedure of the network. And please see the paper for the full algorithm and for more details. Let's look at a few results. I'm not going to explain this table, please see the paper, but the cool part and the takeaway message is that because we use normalizing flows, we can quantify and measure whether and by how much we manage to tame the model. And indeed, we managed to forget an identity. We managed to do it better if the forget set is larger. Here in the table, we show forget sets which contain 1, 4, 8, and 15 images. And that's the important part, or one of the important parts, the process is fast. Here, taming took less than 1% of the original training time of the network. Besides forgetting a specific identity, we can also forget attributes, such as decreasing the chance for a specific hair color or face feature. Here we show how we manage to change the distribution of many attributes as a function of the number of taming steps. For example, this specific point indicates that after about 80 steps, we managed to change the output distribution from mostly no beards to about 50% beards. Let's see some visualizations of these changes. Here we reduce the chance of producing blonde hair. The video is showing the outputs throughout the taming process. Here we increase the probability of two attributes at the same time, smiling and blonde. Obviously, there are limitations. First, our method requires an explicit PDF, probability density function. This was a conscious choice so that we can explicitly reason about probabilities, but it also means that if we want to adapt our method to different generative models, we really need to change it. We can no longer rely on an explicit PDF. Second, we are using a remember set, which means that we require access to data from a similar distribution to the data that was used to originally train the network. Sometimes you don't have that. With that, I want to really thank you for listening. That's it for me. Please check out our paper, our code. Thank you very much.